Hello, everyone, and welcome back to calculus. So today we're talking about improper integrals. So far what we've done is we've used integrals to find areas of finite regions under a graph. What we're trying to do today is we're going to adjust this process to be able to find areas where one side of our region is actually going to be infinite, one or more sides of our region. So what exactly do I mean by this? Okay, so here is an example of sort of the difference of what's going on. So in this leftmost picture, this is a finite region. It fits within a small finite box, that area that we're finding. And so we've been doing integrals like this. If this is the function f of x, then that area, it looks like it's the integral from 2 up to 5 of f of x dx. And we've been figuring out how to calculate these kinds of areas so far. But we haven't seen pictures that look more like these, where kind of think about my picture going off to infinity, right? So I've got a region that is going to be infinitely long. It's getting shorter and shorter in this picture, but it's still going off all the way along the x-axis. Or in this picture, I'm thinking about the area under my graph, and where I see sort of an infinite length is as x is getting closer and closer to 0, my function is going off to infinity, and so my shape sort of has infinite length in that direction, in the y direction. So if I use our same sort of function or integral notation, looks like I'm trying to do the integral from 2 to infinity of f of x dx here, and the integral from 0 to 5 of f of x dx here. So that's sort of the notation that we want for our areas, but we just don't know quite how to handle these pictures yet because we've got some sort of infinity going on in the picture. It's worth noting, so we've done, again, these first integrals before. These are called definite integrals. Integrals where you have a sort of finite area or finite portion of the graph or the plane that you care about. And these are going to be called improper integrals. Any integral where we have some sort of infinite side length. Okay. Now, it's worth mentioning that just because we have an infinite side length, the area might not be infinite. So if you look again at this picture, sure, we have this side length going off infinitely, but the height is getting smaller and smaller and smaller. So maybe we've actually somehow managed to get a finite amount of area, but just stretched it out infinitely far. On the other hand, it'll be really easy to also end up looking at something that has an infinite side length and an infinite area. So we might actually see finite amounts of area or infinite amounts of area in these problems. Okay, so that's kind of the intuition of what's going on here. If I go a little bit more carefully, the definition of an improper integral is where either one of the integrands is plus or minus infinity, or where our function is continuous on the open interval between the integrands, but maybe it's not continuous at one of the integrands, or it could be both. So, for example, in this picture, this is an example where one of my integrands is plus or minus infinity, so that's why this integral is an improper integral. And then in this picture, my function is continuous on the open interval 0 to 5, but it's not continuous at x equals 0, because we've got an asymptote going on there, and so that's why this integral is an improper integral. Okay, so those are sort of the warning signs that we're going to look for is infinite bounds, infinite integrands, or places where our function is not continuous at. Okay, and how are we going to do this? Well, per much of calculus, the answer is use limits. So what we're going to think about is this full picture. Well, okay, that full area, right, which is, write it out in interval notation. So if I want really the area from 2 to infinity under the graph of f of x dx, then, well, what I could do is I don't know how to handle that infinity, but I would know what to do if I like cut it off at 5, right? I could find the area from 2 to 5. I know how to handle that. Or maybe I cut it off higher. Maybe I cut it off at 6. Or I cut it off at 8, and so forth. So I can kind of keep looking at more and more of my picture. And as I add in more and more in my picture, I'm getting closer and closer to the overall integral. In other words, what I'm saying is, I integrate from 2 to infinity of f of x dx. Well, if I cut off at any sort of x value a above 2, that would be an approximation for the overall area. It might be a really bad approximation. For example, integrating just from 2 to 3 is not a good approximation for integrating from 2 to infinity, but still, it's an approximation. And we can make our approximation be better and better as we let a go off to infinity. And so instead of just thinking about that approximation, what we're really going to do is we're going to take the limit as x goes off to infinity. Or sorry, a goes off to infinity. And do the integral from 2 to a. And so we're going to be taking a limit of something that we know how to do. We know how to solve out this integral. It's going to give us some sort of function in a. And then we'll think about taking the limit of that function in a, and that'll give us a number overall. Okay, so let's see this in practice. So I'm being asked to find the area under the graph of 1 over x to the 4th. And I'm asked to look at the region between x equals 1 and x equals infinity. So if I graph my function, so this is the graph of 1 over x to the 4th, and I highlight the relevant region. Okay, it's going to be hard to see on this graph because the graph goes to 0 pretty quickly, but we're going to have sort of an infinite length section that has a little bit more visible area at the start, but then it's going to be just really, really small heights as we go off to infinity. So I'm trying to find the area of this blue shaded section. Okay, obviously an improper integral because I've got infinity as one of my bounds. And so that's going to be the thing that I replace by a limit since that's my issue. So I should really think about going up to infinity or letting my bounds get closer and closer to infinity. And I'm instead just going to integrate up to a. So I'll take finite amounts of the area, and then I'll think about what happens as I let a get bigger and bigger. So again, that's essentially saying, oh, well, I could cut off my picture there and just look at this area, and that would approximate my full integral. I'd get a better approximation if I cut off here, and so look at all of that area. Better integral, or better approximation if I cut off further and further and further. That's the idea. Okay. Now for a second, we're going to forget about the limit. Let's just make sure you keep it in your notation. But for a minute, all we need to do is figure out that integral. So if I want to figure out that integral, I'm going to write it a little bit nicer so that I can think about how to antiderive it. right? So I probably got to x to the minus 4 via a power rule. So if I write it as a power, I'm going to be able to think about anti-deriving it better. And so really, when I just calculate that integral, that's the same as, let's see, the antiderivative should be x to the minus 3. I need to raise the power. And then if I multiply it by negative 1/3, that'll make my constants be right in the end. Plus c, evaluated at a and 1. So again, all I've done in that last step is I took this portion, my integral, and I evaluated it. I anti-derived and plugged in my endpoints. Okay. So if I clean that up a little, this is the limit as a goes to infinity of, okay, negative 1/3a cubed plus c minus negative 1/3 times 1 cubed plus c. My plus c's cancel. I'm left with the limit as a goes to infinity of negative 1/3a cubed plus 1/3. If I look at this, think back a while to our limit laws, I know I can move my 1/3 out of the limit. And so really I only need to think about what the limit is as a goes to infinity of negative 1/3a cubed. And if you think about that, your denominator is getting larger and larger. Your negative numbers the whole time, but your denominator is getting larger and larger. Your numerator is staying the same. And so in total, that fraction is going to 0. And so that limit is going to be 0 plus 1/3. And so in total, what we see is that our area is 1/3. So the total amount of area under this graph between 1 and infinity is just 1/3 units squared of area. All right, so that is our first example. Let's do one more example and then I'll let y'all try your own. So example 2, we're going to integrate the same function, but we're going to integrate from 0 to 5, because that's going to give us our other type of improper integral. So in particular, if I look at my picture again, and I think about what area I'm trying to find, so I've got the graph of my function. I should be looking at x equals 0 up to x equals 5. And so this is the area of my picture that I'm trying to find, is that blue shaded region. I overshot it a little, but yeah, that region. Okay. So the thing about this that's making it improper is the side where x is 0. So that's going to be the piece that I replaced by a limit. So I should take the limit as a goes to 0 from the right, a to 5, 1/x to the 4th dx. This intuition is a little bit different. I mean, it's the same sort of thing. We're going to just take sort of integrals that we know how to do and take the limit of them. The difference in what we're doing this time is we are thinking about sort of cutting off our picture from the left side. So instead of doing this full area, maybe I just find this much area. And then I keep going and I let my a value get closer to 0. So then I'll increase and I'll find that much area. Then maybe I let my a value get even closer to 0. And so I keep adding on more and more of my picture, hence why my full picture that I want is equal to the limit of letting a go down to 0. Okay. So that's what we're trying to do. All right, so again, same process, I'm gonna just hold on to my limit for a second and not think about it too much and deal with my integral first. So as we said in the last problem, the antiderivative of that function is negative 1 over 3 x cubed plus c. And again, I'm evaluating it at 5 and a this time. So I'm looking at the limit as a goes to 0 from the right of negative 1 over 3 times 5 cubed plus c minus negative 1 over 3 a cubed plus c. So just plugging in my bounds there. Then I'm gonna clean this up a little so my plus c's cancel. And so I'm looking at the limit as a goes to 0 from the right of 1 over negative 375 plus 1 over 3a cubed. And again, I can move my constant out of the limit because of the, I guess in this case, the sum rule is what's letting me bring this out, the sum and the constant, or the basic laws, limit laws. So really the part that I need to think about is this limit as a goes to 0 of 1 over 3a cubed. If you think about that, as a is going to 0, your denominator is getting smaller and smaller. So you're taking 1 and you're dividing it by smaller and smaller positive things. So what's happening in total is your fraction is going to be going off to infinity. And so infinity minus 1 over 375, still going to be infinity. And so when we get cases like this, right, what we interpret that as is saying that we have infinite area that we're trying to look at. So this shaded region has just enough sort of width to be able to be infinite. And some other sort of wording that you might hear in these cases is that this integral does not converge. Or you might get a D and E. Those are things that all indicate that you got an infinite area. Okay. All right. So I'm going to have y'all try a problem yourself. So you're looking at the function 1 over x, and you're trying to find the area of it between negative 3 and 2. And the hint is we first need to break this into two improper integrals. So it looks fine, right? It looks proper because we know 1 over x is continuous at minus 3 and continuous at 2. And we know it's those bounds obviously aren't plus or minus infinity. But oops, sorry, jumping ahead here. But if we think about it and we graph that function, then we have a discontinuity at x equals 0. So what you'll need to do is you'll need to think of this as two different improper integrals. You need to do the improper integral that includes 0 from the left side, and then the improper integral that includes 0 from the right side. So you should go forward now and do the techniques that we've been talking about on this integral and this integral separately. All right, so I will pause here for a moment and give you a moment to think about this. Pause the video and try this problem. Okay, hopefully you actually paused and tried this problem. I claim that for this, this integral, you should have ended up with negative infinity. And for this integral, you should have ended up with positive infinity. It's super tempting to say that the answer is 0. That's not what you should say, because we can't infinity is not a number. We can't combine negative infinity and positive infinity in that way. There's sort of different sizes of infinity, and so we're not going to make any guesses about how these two combine. And instead, our answer is just that this does not converge. So if you ever break your problem into multiple pieces and even one of them doesn't converge or is infinite in some way, the full problem does not converge. All right. Fantastic job, y'all. And I will see you in class soon.